as long as we are meeting. So, okay, so back to the notes. So this is where we left off. So again, if you missed something, and again, I'm kind of spending some time doing this. I kind of got trying to think of who was in here. Tyler was in here. So if Tyler's awake, he could confirm this. Yesterday with my chemistry class, I went to great extent. So did Mr. Conyers and Mr. Hodes, kind of doing, we did the flame test in class. And then outside of class, we used to do the spectroscope lab. And if you remember that from first year chem, where you would look through a slide and you'd see these color patterns. Do you remember this at all? But because of time, we weren't able to do it. So we went, Mr. Conyers, Mr. Hodes did really most of the work, but we had a whole thing that they could watch online. And half of them didn't even do it. I was so pissed off. And I do the same thing with you guys. I'm trying to take these things, and it takes me some time outside of class, and hopefully it's a benefit to you guys. Okay, so Kara, can you guys see this again at home? Can you see those notes?
Yes.
Okay, perfect. Okay, so we already talked about this page. Definitely a key thing. Okay, moving ahead now, and like I said, I got it here. I'm just going to do this joke now. What is important on this slide? Again, going through the math, the derivation of this. So now I'm going into new territory. The derivation of this is not important. Okay, but what is important, and this is on the formula sheet, is where it says rearranged to T1 half is equal to 0.693 K. Okay, we're going to do a problem here. This is actually on it's on the formula sheet. So for those that are taking notes, I'll give you time. But this, again, on the formula sheet, so you guys can take time if you want to, and I'll point this out again. So under kinetics, it's the third equation. T1 half is half-life. Half-life. Okay, so for those of you that are listening online, here we go. I always wonder when I get sarcastic like that, who hears me? Okay, I've only got one joke today, David, so here we go. See if you remember this one. The IRS, I think I told you this before we shut down last year, decided to audit Grandpa. The IRS is the Internal Revenue Service. They are like the tax people, so they are kind of widely hated. They decided to audit Grandpa, so they summoned him to the IRS office, and the IRS auditor was not surprised when Grandpa showed up with his lawyer. And the auditor said, "Well, sir, you have an extravagant lifestyle, but you have no full-time job, which you explained by saying that you win money gambling. I'm not sure the IRS finds that believable." Well, Grandpa says, so there's three people in this joke, Kennedy. There's the Grandpa, who's there, been called to the IRS office. There's the auditor who works for the IRS, and then there's the Grandpa's lawyer, okay? So Grandpa said, "Hey, I'm a gambler. I can prove it to you. How about a demonstration?" Well, the auditor thinks for a moment and says, "Okay, go ahead." So Grandpa says, "I'll bet you $1,000." I got to take my mask down for a second. Is that okay? I got to use my mouth for this joke. Grandpa says, "I'll bet you $1,000 I can bite my own eye." The auditor thinks for a moment and says, "Okay, I'll take that bet." So Grandpa removes his glass eye and he bites it, Kyle. You want $1,000. The auditor's jaw drops. He can't believe it. Grandpa says, "Okay, now I'll bet you another $1,000 I can bite my other eye." Now the auditor can tell that Grandpa isn't blind, so he says, "Okay, I'll take the bet." Grandpa removes his dentures, bites his other eye, puts his dentures back in. The stunned auditor now realizes he has wagered and lost all these thousands of dollars, and with Grandpa's lawyer there, Kennedy, as a witness. So he starts to get nervous. "You want to go double or nothing?" Grandpa asks. "I'll bet you $6,000 that I can get on one side of your desk. I get on one side of your desk, and I can pee all the way across your desk into your trash can over here on this side of the desk, and I won't get any pee on your desk at all." The auditor thinks, this is an old guy, okay? "You're going to stand over here, and you're going to pee all the way across my desk into my trash can. You're not going to get any pee on the desk at all." Did I tell you this last year? You remember this one? And so the auditor thinks twice and says, Okay, I'll bet you $6,000 that there's no way you could possibly pee all the way across my desk. So Grandpa does, so they bet. So Grandpa gets over here and he pees, and he does pretty good. He gets a whole bunch of pee into the trash can, but then he can't, and then he pees all over the desk, all over the auditor's desk. And the auditor goes, woo, yeah, starts celebrating, whooping, hollering, Chloe going nuts, high-fiving, and Grandpa's attorney moans and puts his head in his hands. And the auditor goes to the lawyer, are you okay? Not really, the lawyer said. This morning when Grandpa told me he'd been summoned for an audit, he bet me $25,000 he'd come in here, pee all over your desk, and you'd be happy about it. I thought that was a pretty good one, Kyle. That was a good one. Chloe, that was a good one. That was good. Okay, now we're all back to chemistry business. Jackson, isn't it good you were here today?
Absolutely.
I wonder how many at home heard this joke. I know Kara did. I don't know if anybody else, none of the other ones did. Okay, so half-life. Now remember what half-life is. This is something that, again, in a normal year, so if you had chemistry 2 years ago, this is something here at our school we always get to right at the end of the year. Half-life is the time it takes for 1/2 of a radioactive sample to decay. And so what I always show my students in first year Chem, and of course last year we couldn't do it, but I always have them set up a table of time and amount just to understand how half-life works. So at time 0, let's just say we have 100 grams. Well, after the first half-life period, we cut it in half. Well, after another half-life period, we cut it in half. And another half-life period, we cut it in half. That's what half-life is. It's the time it takes for 1/2 of a radioactive sample to decay. And I'm going to show you on the next slide that there are many different isotopes, and some have half-lives of seconds. So they go through, they react very fast. And some have half-lives of tens of thousands of years. And this is a big issue with nuclear energy, because nuclear energy produces many radioactive isotopes that they have to be disposed of. Some have half-lives of seconds or minutes, so they're kind of gone real fast. Some have half-lives of tens of thousands of years. And the question is, what do you do with those? Where do you put those? And our government decided like 30 years ago to bury them underground about an hour north of Las Vegas. And this was back in the 1980s, but they never buried any there. But the point here is, what is half-life? Half-life is the time it takes for 1/2 of a radioactive sample to decay. Now, so half-life of a first-order reaction, and that again is important, the time for 1/2 of a radioactive or of a reactant to convert to a product. Now, this stuff here, the math stuff, the rearranged, you don't need to know that. But where it says rearrange to, so those of you that are listening at home, the T1/2 is equal to 0.693 K. So again, back on your formula sheet, this might be something you might want to write down. So where it says kinetics, the third equation, so T1/2 means half-life. And you might even want to note that. That is half-life. It's equal to this little equation that is 0.693 K, where K is the rate constant. So T1/2 is equal to 0.693 K. So again, nothing that you guys have to memorize. K is the rate constant, and this is the half-life. And this is for first order. So on our test, I'm sure I have it on our quiz. On the AP test, when you see half-life, which I bet you'll see on whatever day it is, in May 7th or whatever, but number 6, I'm looking at the quiz, there's half-life. So to do a problem like I've got here on the board, it's actually really easy, okay? So if you can identify this equation, so whenever you see half-life, you know this. So we're given the rate constant, calculate the half-life. So I'm just going to plug in here. So I've got 0.693, and I just put in 6.7 times 10 to the negative 4 over seconds. And so if I do that on my calculator, again, we're not going to be using calculators too much today. We We did a lot in the last class. Okay, so what I get there is the half-life is 1,034. The unit on this is seconds because this is seconds. Technically, my sig figs are wrong here because there's 2 sig figs. So really, I would want to go 1.0 times 10 to the third seconds. But it's a very easy little calculation. So whenever you see half-life, and there are other equations for half-life for second order and zero order, but that's not on our formula sheet. And because those aren't on our formula sheet, they're not going to give you that on the AP test. Okay, so here in the next slide, and again at home, if there's something you can't see, if there's something that you can't hear, just speak up. And same with you guys. There's nothing to copy down here, but one thing to note on this slide is, so what I've got here is you can see the half-lives in this column, and then you can see the rate constant. Note that these are inversely related. So as the half-life decreases, the rate constant increases. And that's really what you should note off of this page. So as the rate constant, the lowercase k, and the half-life have an inverse or an opposite relationship. And so that tells us, okay, well, what does the rate constant mean? We go, what does the rate constant mean? Well, the bigger the rate constant is, the smaller the half-life, which means the reaction is going faster. So a big rate constant, a large value for the rate constant, is telling you that the reaction is going faster, and a smaller number for the rate constant means that it's a slower reaction. You can see some of these have half-lives truly in the millions of years. Uranium-238, there's carbon, so that's 1,000 years, and some of these have like 10 to the negative 7 seconds. So we're talking like microseconds how fast some of these react. Okay, now second order reaction. Now let me put this up, and again, I'm kind of just going through what is really important on this slide. So what's important here is really the bottom is what's really important here. And this is also on the formula sheet. Okay, so in notes here, and let me just talk briefly, and then I'll give you guys that are taking notes time to write this down, and then we'll come back and we'll talk about this. But second order, you guys, I think, hopefully know what that means now. So it could be like this. And when it's like this, when we have A to the first, B to the first, which is a very complex integrated rate law, this one you'll deal with in college. But you understand that that's second order. But if we're looking at this, and again, the calculus, the derivation part, you don't need to know that. But then here on the bottom of the page, it's on the formula sheet, and it's down here on the bottom. And you might want to identify that the middle one where it says kinetics is the second order integrated rate law on your formula sheet. Okay, so again, you might want to write down number 1, number 2, but the calculus part, you don't need to know, but this is the key thing, the bottom. I'm pointing at the bottom, which is on the formula sheet in the kinetics. It's the second equation. Okay, I'll be quiet here for a second and give you guys time to write this down. Like I said, that AP chemistry is not a class that is, you just have to been through algebra, there's not going to be any trig or calculus in AP Chem. They'll never ask you to do any derivations. And to be honest with you, a second order, I'm going to do a second order problem here. We'll do one. It's the one place you're going to need a calculator today. But the second order rate law does not come up very often. And I think on the AP test as well. Understanding what it is, and with the differential rate law, but the integrated rate law, it's not as much. So again, on your formula sheet, and I'm telling you this, I would do this if I were you. So if you're on the front, and again, for those of you that are listening at home, down here in the bottom left-hand corner where it says kinetics, the second one is exactly what I've got on the board. And remember, the A sub T is the ending concentration. The A sub 0 is the initial concentration. And so you, again, on your formula sheet, you could say this is the second order integrated rate law. And, you know, if you ever think about, oh, man, AP chemistry, this is a hard class. But if you were to tell your parents or your friends, you know, we've been dealing with first and second order integrated rate law in AP chemistry, and they would be like, what in heaven's name are you talking about? So we're doing some definitely some challenging stuff. Okay, so again, I would note that on your formula sheet. Okay, so then here we go. I want to just do one problem. The half-life here is something that I'm not going to hold you to. This is because it's not on our formula sheet. So what's on the top of this slide is just again going through the mathematical derivation. It's not on our formula sheet. It's not going to be on the AP test. It is not on our test, okay? But if you wanted to note that, because, you know, when seniors, you go to college next year, if you take chemistry, you'd probably, maybe they'll actually have college like normal. I don't know. Who knows? Probably things will change. But in juniors, if you go to college, you know, and you take chemistry 2 years from now, they might have this. So I'm just going to leave it up. But I'm going to tell you, for us, it's not going to be there. But then I do want to do this problem. But this is the half-life, what I've got on the top of this slide. This is the half-life of a second-ordered equation. But for you guys, for right now, if it's ever a half-life problem, it's assumed it'll be first order. Because that's all on our formula sheet, so that's all I'm going to give you. Okay, and then we'll go ahead and do this problem. Again, I don't think I have a problem like this on our test or on our quiz, but just it's really not a difficult one to do. So again, I'm just going to take a second here and let you guys copy this down. For the Mason.
Like on tests and stuff, will the problems cause in second order, or will
They'll tell you. Yeah, they'll tell you. Like Mason, Mason asked, will a problem tell you? And it will. Like on the quiz, and if you had it out, Mason, you'll look like, if you look at number 4, the back of the first page, it says the decomposition of a certain insecticide in water is 12 degrees Celsius, follows first order kinetics. So they're telling you it's first order. And so you're going to do that. You're going to do that problem, number 4, A and B, exactly like what we did yesterday. But then if you look at number 6 on the next page, it says the reaction of C4H9Cl with water is a first order reaction. So when they tell you the order, they're telling you to use these equations which are on our sheet. Okay, that's a good question. Okay, so again, the mathematical equation we've got here, this is for second order, and this is on our formula sheet. So again, you don't have to memorize this, you just have to use this. Okay, so again, AT is the ending concentration. A0 is the initial concentration. K is the rate constant. And T is time. And just like the problem that I did yesterday with the first order rate law, you have to make sure the units agree here. And that is the case here. The units do not agree. So I'm doing problem A. I'm going to wait one more minute for those that are taking notes. So again, to Mason's questions. So again, what's on the top here? Again, this is again if you're planning on taking chemistry in college, again, some of it depends on how you do on the AP test. But that'll come up. It's not going to come up for us. But then the problem. So to your question again, Mason, see how it says second order? They're telling you it's second order. They give us the value for K, and it's molarity per second. So the value for K is 7.0 times 10 to the 9th. So that means, so if we think about this, remember I just said, what does the value for the rate constant mean? Well, a big number for K is telling you this is reacting really fast, has a small half-life. A small number for K means it's reacting very slow. But the time they give us is 2 minutes. Well, that doesn't align with seconds. So I need to get the 2 minutes into seconds. And I did that in that problem that I did yesterday. So I want to get my units to align. And that's usually here with time. Okay, so now I'm going to put this here. So the seconds will cancel out. And then it says, so that I have plus 1 over A0, which is 0.086. And the question here is X. What is the ending concentration? Okay, take a minute and see if you guys can get the actual to the final answer. So there was a conversion, just making sure the units align right. And then you want to plug everything in and solve. Okay, and this is, I think, the one place today where you need a calculator. Eight, 4, I'll come back and round at the end, but this would be again 1 over molarity. So if I add those up, it's not going to affect us at all. So I have 8.4 times 10 to the 11. 1 over molarity, 1 times X. So then if I cross multiply, what I get is 1 over 8.4 times 10 to the 11th, 1 over molarity. So my unit here, 1 over molarity.
Mr. Wood, would you be able to move the camera down a little bit?
Yes, Carol, thank you for saying that. Is that better?
Yes, thank you.
Kara's listening. Oops, 10 to the negative 12. And the unit on this would be molarity, and at this time, the unit works out right. David asked such a good question on lab, I didn't really have a good answer for him. Here the unit works out. And then and a lot of times we do our AP chemistry problems, really all the time we're doing numbers. We should go back and ask ourselves, does that make sense? Well, this is a really small number. Well, if we have a large value for K, this reaction is going really, really fast. So that does make sense. 1.2 times 10 to the negative 12. Okay, so that is the second order integrated rate law. That does make sense because the value is so low. Okay, we're not going to do the half-life problem. Okay, so what is key on this slide now is what's in the middle. So a second order reaction will be linear if 1 over the concentration of A is linear. So again, and I've talked about this already, and at the Penny Lab, you guys are going to do this. But we're going to do graphs. So when we're given concentration versus time data, we're going to do graphs. We're going to do 3 graphs. If it's the natural log versus time that's linear, it's first order. If it is the reciprocal of the concentration like this versus time that is linear, then it is second order. So second order reaction will be linear if 1 over A versus time is linear. So we're going to do graphing. So in concentration versus rate data, we're going to do concentration versus rate. We're going to do the ratios, like what we did last week. That's how we're going to figure out the order, the X and the Y. When we have concentration versus time data, we're not going to do the ratios, we're going to do graphs. And we're going to look for the straight line relationship. So what gives a straight line relationship is the natural log of the concentration versus time. It is first order. If what gives the straight line relationship is the reciprocal of the concentration versus time, then it is second order. So on the next slide, nothing really to note here other than what I just said. So if you look at the 2 graphs, and this is what you guys are going to do. A matter of fact, let me just keep going here. But if we've got the column on the left at the bottom is concentration, then we have the middle or the second column is the reciprocal, and then the third one is natural log versus time, and we're going to look at those graphs. Well, the graph on the right is the reciprocal of the concentration versus time. So this is a second order reaction because what gives the straight line relationship is the reciprocal of the concentration over time. One thing I don't have written down here that you should note too, and I've said this already, you just take the slope of the line. So whatever the slope of the straight line is, that is the rate constant. So I'll say that again, okay? So the rate constant, when you're doing these graphs, is determined by the slope of the line. And if it's a negative slope, you just take the absolute value. Okay, so here, what is the order of this reaction? So I'm looking for the straight line relationship. So you're going to do a lot of graphing. So to me, it's almost like you got to be kidding. The way you figure out the order of the reaction is you do graphs. Yeah, you do. And so if it's the concentration versus time that's straight line, then it's 0 order. And I'm going to talk about that in a second. If it's the natural log versus time, that gives a straight line, it's first order. And so the answer to this question, this would be second order. And how I know that this is second order is what gives me the straight line relationship is the reciprocal of the concentration of the reactant versus time. So we're looking for the straight line relationship. And so then here now is 0 order. So 0 order, so the rate of K, the rate equals K, and it is independent of the concentration. What would the graph of the concentration look like? Okay, so 0 order. If I have the concentration versus time, it would look like this. That is if it's 0 order. So again, to me, it's almost like it's kind of like you got to be kidding that. So it'll just be a little bit of a painful process. It'll be some graphing. Okay, and I'm actually going to give you here, this is from our book, this table. And again, I'll slow down here, give you guys a couple minutes to write this down. But I'm going to put up, again, going back to the AP biology, AP chemistry teacher in Bozeman, Montana. I'm going to kind of give you his little flow chart here. But this does a good job of kind of reviewing a lot of what we've talked about already in this chapter, especially the integrated rate law. So I'm just going to write on the board, and this is, again, comes right from the guy at Bozeman, Montana, and I just think it's kind of just simplifies it all. So rate is equal to K times A to the X. So we've got 0 order. We've got first order. And we've got second order. And so, so for 0 order, we have rate is really just equal to K, because if something's raised to 0, it is just 1. And so what gives us the straight line relationship then is the concentration versus time. Okay, so here, first order, rate is equal to K like this. And so if we did a graph of the concentration versus time, we did a graph and its first order, it would look like this. But what gives us the straight line relationship is the natural log of A. Kara, do I need to move this down? Can you see that, Kara?
Yeah.
You good? Okay.
Yeah, that's good.
So then second order, and again, the second order that we're going to deal with is this. Whoops. Rate is equal to K times A squared. That's what we're going to be dealing with this. Like I said a few minutes ago, if you guys take chemistry beyond our class, you deal with this. And to be honest with you, I can't remember this. But when we're talking about second order, we're talking about it like this. So we did a graph of change in A versus time. It would look even more slope than this. But then what gives us the straight line relationship is 1 over the change in A versus time. It actually looks like that. And remember, the rate constant is determined by the slope of the line. And so when you guys have a problem, like on the quiz, if you look on the quiz, like number 5, so they give you concentration and time data. And the question is this reaction first order or second order? Well, what you're going to do is you're going to do a graph. You're going to do a graph, and you're going to look for the straight line relationship. This is going to happen on the test too. Okay, so it's not like it's hard. It just takes some time to do it. That's what you're going to do on the Penny Lab. The Penny Lab, you're going to graph. You're going to do this graph, and this graph, and you're going to look for the straight line relationship. So whichever one, so if the straight line relationship is the amount versus time, then it's 0 order. If it's the natural log of the amount versus time, then it's first order. If it's the reciprocal of the amount versus time, then it is second order. And the way on the penny lab you're going to figure out the rate constant is by taking the slope of the line, just taking the absolute value. It's not too bad, Jackson, not too bad. Okay, so now moving ahead, we're doing good. Okay, so just going back now, let's review the units on the rate constant. So we are through now the two main the two really main points in this chapter, which is the differential rate law, which is the ratios, which is concentration versus rate, and the integrated rate law, which is graphs, concentration versus time. And the half-life is in there. So those are the main things in this chapter. Okay, so I'm going to leave this on the board. I don't know if it's valuable or not. And I kind of restated the same thing multiple times. But really, it's not too bad. You just got to do some graphing. Okay, this slide is just reviewing the units because once in a while, I still haven't made up the test for this year, and this usually in a normal year, I just have a test on chapter 12 and then just a test on chapter 13. But for the sake of time, I'm going to combine those two. And then I asked Juliana to make a prediction. Are we going to come back full time or not? Who knows? But then if we come back full time, will we go back to our old schedule? Who knows that too, right? But if we come back full time and we have the test after spring break, and then it would just make a little less crunched for the day of the test. But on the chapter 12 test, sometimes when I'm making up the test, so for your older siblings, the clue I give them, like Mason asked earlier, does it tell you in a problem? Well, sometimes it does. But sometimes I don't tell you, but you look on the units of the rate constant. So let's just review this. So often the unit of the rate constant can be used to determine the order of reaction. Okay, so here's another way. And Mason, usually I'm not that evil where I just expect you to know that. But this is a little clue in the problem that the units on the rate constant can tell you the order of the reaction. So let's just review this. So zero order, so these are the units on K, the rate constant. I've already done this. This is all new. This is new stuff. So let's just make sure we're good with this. So zero order.
Mr. Wood, would you be able to move it up just a little bit?
Thank you, Kara. Can you see my hand now?
Yes, thank you.
Thank you for saying that. It is molarity per second. This is the units on the rate constant. First order is 1 over seconds, or some unit of time. Doesn't have to be seconds. Second order is 1 over molarity times seconds. Third order is 1 over molarity squared times seconds. And hey, I keep kind of adding to your formula, or to your formula sheet. But you might want to write this down right here, somewhere where it says kinetics, the units on the rate constant. You might even want to write down it is zero order if it's concentration versus time. It is first order if you got the natural log of the concentration versus time. It is second order if you got the reciprocal of the concentration versus time. You might want to write that down along with the units on K. I'll let you guys use it on the test. I probably I'm the bad AP chemistry teacher because, but my thing is as we get closer to the AP test, the formula sheet can be a really good kind of review of a lot of the main things. So, and if you ever lose formula sheets, I've got some right up on top of the filing cabinet. So often the rate constant can be used to determine the order of reaction. So for first order, second order. So the answer there, so the question, what order is a reaction with a rate constant? So that would be, that would have been a third order reaction. So the answer would have been third order. And there are some problems. So you guys have a lot of chemistry that you guys can be doing now away from here. You got problems in the book. You now have 2 reviews. All the answers are included. You got the quiz, you got the labs. So there's a lot of things you can be doing. Let me do one more page. Okay, and this is where we'll stop for today. And now we're going into the last topic. And I don't think this is as big a topic. And this is a topic, again, where in a normal year last year, we would have covered this well. So if you had chemistry 2 years ago, we did, but because of the virus and everything. But this is going to be about activation energy diagrams and these things called reaction mechanisms. And this is definitely something that is fair game for our quiz, our test, and for the AP test as well. So activation energy. So remember what activation energy is. It's the minimum energy required for when 2 molecules collide. Okay, so this is where I'm going to start tomorrow. So let's go ahead and get this copy down. We made good progress today. And I think by the time, I'm really hoping tomorrow, and again, tomorrow we need to be really efficient, but tomorrow I'm hoping we could get done or really, really close to done. By Friday, we'll be done. And hopefully Friday we can maybe move into chapter 13. Remember, test corrections for everybody Monday. So you got today and Monday for those that are here. For those that are home, you got tomorrow and Tuesday. And if you want to bring in paper towels, you guys have, again, you can bring in them today or Monday to do that. So, okay, I think the bell's going to ring here in a minute. We did good today. You guys did good. You're champions. But Jackson, Samantha, I had a pretty good joke today. See you guys. Good job.
Thank you.
See you, Kara. See you guys.
Mr. Wood.
Yes, Allie.
Hi. I am just asking real quick. I was gone yesterday, which I know you noticed, but I just had like a doctor's appointment that I literally forgot about. I know I probably missed. Wasn't there like part of a lab that we did yesterday?
There was a lab, and we will. And Allie, your lab group, Tyler and David and